Subscribe to the channel and hit the bell. I'm your host, Dragon Megalodon, and welcome back to the only explainer you'll ever need to decode the math that's literally running our world. Today, we are cracking the algorithm behind compound interest and logarithms. So let's just dive right into this codebase.
All right, jump straight into the terminal with me. Imagine we need to build a function, right? We've got an initial parameter of $200, and it's compounding at 3% every single year for 10 years. Now, because that 3% is being added annually, the logic here is basically just a loop. The money sitting in the bank gets multiplied by 1.03 each and every year. So, after 1 year, it's 200 times 1.03. After 2 years, it's 200 times 1.03 squared. We run that loop 10 times for the 10 years, and our output evaluates to exactly $268.78.
But hey, what if the system updates more frequently than that? Let's frame this like a trace table in a debugging session. Say you initialize with $300 at a 4.5% annual rate, but it computes semi-annually. That means twice a year. So we take that 4.5 divided by 2, and that gives us 2.25% per iteration. If you trace the logic, you'll see the function multiplies the base value by 1.0225 every single half-year step. So by year 1.5, which is exactly 3 iterations in, we're actually cubing that multiplier.
Let's abstract this into our core formula. This brilliantly illustrates the ultimate compound interest equation. P of t equals a times 1 plus r over n, all raised to the power of n times t. Let's break those variables down really quickly. A is our initial amount, our starting parameter. R is the annual interest rate, which we pass as a decimal. N is the number of compounding execution cycles per year, and t is the time in years. You're going to want to memorize this formula. It is absolutely crucial. It's the back-end logic for almost all modern financial systems, from your bank accounts to your loan payments.
Now, what happens if we push the hardware to its absolute literal limit? I'm talking about compounding infinitely, 10 times, 1,000,000 times a second. When you hit the limit of compounding more and more frequently, you achieve continuous processing. We completely replace our standard loop with the continuous compounding formula. That's P of t equals a times e to the power of r times t.
The absolute key here is this magical number, 2.718. You probably know it as Euler's constant, or simply just e. You need to treat e as the ultimate continuous growth variable. For example, if we input $4,000 at a 2.5% annual rate for 5 years directly into our continuous formula, we just calculate 4,000 times e to the power of 0.025 times 5. Boom! We instantly get an output of $4,532.59. No loop required. But here's where we hit a bit of a snag, which brings us to the main complication of this explainer. Okay, so we know exactly how to scale up exponentially using these variables, but what logic do we actually use to reverse the whole process? Like, if we already know the final output, how on earth do we isolate the exponent? How do you reverse engineer the exponential function itself when the unknown variable you're looking for is stuck way up in the power?
Enter the logarithm. This right here is your ultimate reverse engineering tool. When you see the expression log base a of b equals c, it is essentially asking you one highly critical question. It's asking, what power do you raise base a to in order to get b? That's it. The logarithm's entire job, its sole purpose in life, is to isolate and return the exponent as its final clean answer.
Let's compare the syntax of these two concepts. Think about the exponential format, a to the power of c equals b. Now think about the logarithmic format, log base a of b equals c. Notice how the base, the a, stays exactly the same in both expressions? It's a direct translation. The log perfectly refactors that exponential equation so that the exponent, our c, becomes the isolated output. All right, let's run a few test parameters through this new log function just to see it in action. Take log base 2 of 8. Remember our question, what power do we raise 2 to get 8? Well, 2 cubed is 8, so the answer is 3. What about log base 2 of 1/2? Well, to get a fraction from a whole number base, we need a negative power, right? So the output is -1. And log base 2 of 1, anything to the 0 power is 1, so that just returns 0. This totally proves that our log function can successfully return positive, negative, and 0 integers depending on what you feed it. You gotta watch out for a massive bug here though. This traps beginners all the time. Fatal errors. Attempting to input 0 or a negative number into a log function, something like log base 10 of 0 or log base 10 of -100, is a huge no-go. This will instantly throw a calculator error. Why? Well, think about it. There is absolutely no exponent in existence that you can raise a positive base to that will ever output 0 or a negative number. It's literally impossible. The system will just crash trying to find it.
So how do we actually prevent that crash? We debug the domain. Let's take a complex log function, log of 2 minus 3x. To keep the runtime stable, that argument inside the log absolutely must be strictly positive. Step 1, we set 2 minus 3x strictly greater than 0. Then we just move the 3x over, so 2 is greater than 3x, divide by 3, and we get x is less than 2/3. Simple algebra, but now our domain is hard-coded. X must be less than 2/3, or the whole program fails.
Let's render the visual output of this logic. If we graph y equals log base 2 of x, we get this incredibly beautiful sweeping curve. It always passes right through the point 1, 0. Then it gradually climbs up as x gets larger. But as x approaches 0, those y values, they plummet straight down into negative infinity. And notice, it never actually crosses the y-axis. That is entirely because of the domain restriction we literally just debugged.
So just summarizing the core properties of this graphical interface, the domain is strictly x is greater than 0. The range, on the other hand, covers all real numbers, going from negative infinity all the way up to positive infinity. And that boundary it never ever crosses. That's what we call a vertical asymptote, hard-coded at x equals 0. The function approaches it, gets infinitely close to it, but it will never, ever touch it.
Now, you can totally transform this output visually, too. Let's say we take the natural log, which, by the way, is just log base e, usually written as ln. If we add 5 completely outside the argument, like y equals ln of x, and then plus 5, that entire curve just shifts vertically up by 5 units. But if we add integers inside the argument itself, like y equals log of x plus 2, it modifies the x values directly. That shifts the whole graph, including its vertical asymptote, horizontally to the left by 2 units.
All right, get ready for the ultimate trick. Exponential and logarithmic functions that have the exact same base act as perfect inverses. They literally cancel each other out in the equation. If you have log base a of a to the power of x, it leaves you with just x. Conversely, a to the power of log base a of x also leaves you with just x. They completely delete each other from the equation. It's a real game changer when you're simplifying code.
Let's run a really quick execution of these perfect matches. The natural log, ln, perfectly deletes base e. So ln of e to the power of x simply outputs x. Pretty neat, right? Similarly, the common log, which is just log base 10, perfectly deletes a base 10 exponent. So, what's 10 to the power of log of 1000? The base 10 and the log base 10 instantly cancel, and it outputs 1000. It is incredibly clean.
But hold on a second, I need to warn you about one final syntax error before you go pushing your code to production. If your bases are mismatched, this shortcut completely breaks down. For example, ln of 10 to the power of x does not equal x. The natural log is base e, but the exponent sitting inside it is base 10. They don't match exactly, so they totally fail to undo each other. Always verify your bases.
So, let's wrap this explainer up. Logarithms are your ultimate reverse engineering tools, perfectly designed to crack open exponents and isolate the variables hidden inside. When you pair an exponential and a log with the exact same base, they instantly annihilate each other, leaving you with flawlessly clean code. Now, if you want to understand what the code says before it explodes, hit subscribe. Don't forget to like. This tells YouTube that technical content is still alive. Share this explainer with a beginner coder who desperately needs some help debugging their math. And you, what did the code say in your project today?